So in this lecture, we are going to study what are graphs, okay, and what are the different types of graphs, and if we get time, we will study how to represent these graphs, okay. So basically, before we study what are the different types of graphs, we need to know what is a graph. Basically, a graph is a collection of two sets, a set V and a set E, where V is the set of vertices and E is the collection of edges. So vertices, as you can see here on this slide, are the circular nodes. Okay. So in trees, we call them as nodes or leaf nodes and so on, non-leaf nodes. In graphs, we will call them as vertices. If you call it as a node also is fine, but the actual term that you always use is a vertex. The connection between two vertices is known as a edge. Okay. So therefore, your graph normally represented by the letter G is a collection of two sets V and E, where V is the set of vertices and E is the set of edges. A graph can be of two types, undirected graph and directed graph. So undirected graph basically is something like this, where the edges are not having any direction. Okay, so I can go from V0 to V1 using this edge that is connecting them, or from V1 to V0. So both of them are valid. So therefore, the edge between the vertex V0 and V1 could have been represented in two ways. Okay, it could have been represented using like this V0 comma V1. So that represents the edge between V0 and V1, this edge. Okay, the same edge could be also be written as V1 comma V0. Both these answers are correct if I tell you to represent this edge. Okay, so that's the meaning here, that the edge can be represented either as U comma V or V comma U. Okay. The second type of graph is a directed graph. And you can see here, before I go to the directed graph, they have listed a set of vertices here. There are four vertices, V0, V1, V2 and V3. So set of vertices are represented here. Okay. And then the set of edges of the graph G. So all these edges are represented. Now once you write a particular way, you don't write both the formats. Okay. Here it could have been written as V0 comma V1 or V1 comma V0, but you write any one of them. You do not write both of them. Okay. So you write down all these edges. As you can see, there are 5 edges. There are 5 connections between the vertices. So make sure to note down all of them. So that will form the set of edges. So therefore, you can see in this diagram, it is having 4 vertices and 5 edges. Going to the next type of graph. So basically, a directed graph is a graph where there is a ordered pair of vertices. Okay, what you mean by ordered pair is that a direction is also associated with each edge. Okay, so in ordered pair, if you are considering a pair U comma V, okay, U comma V, then U will be known as the tail and V will be known as the head of the edge. Okay, so for example, you consider this edge here from going from V0 to V1. Okay, this edge here, V0 to V1, V0 to V1. So V0 will be the tail and V1 will be the head. How you come to know? Looking at the arrow, wherever the arrow is touching, that is the head, and the end of the arrow is the tail. Okay, so this will be the tail. So you can write this edge only in one particular way. Okay, so the arrow goes from V0 to V1. The direction is given. So therefore, you cannot write it in both the particular ways. So like you were doing for undirected graph. So here you can write it only as V0 comma V1. If you are to write like this, V1 comma V0, it is wrong. Okay, it is wrong because this is the direction. This is the direction given in the graph. Similarly, here you can see the edge is going from V1 to V2. So therefore we will write V1 comma V2. Okay. Set of vertices is all the vertices that are there in the graph, like V0, V1, V2, V3 and V4. So like that you have to list down all the vertices and the edges. So you will get all the particular set of vertices and set of edges for the graph G. Okay, so you need to remember the difference between undirected and directed graph. In undirected, there is no direction. Okay, the edge can be represented in both the ways. But when you write the answer, you have to write only one of the ways. Okay, U comma V or V comma U. So you write any one of those. You cannot write both. Okay, but in a directed graph, you have to write the edge only in the direction of the arrow. You cannot write in both the ways. So therefore, you get one clear-cut answer. Okay. Now let's look at the various definitions that are associated with the graph. As I'm telling you, please note down, okay, as fast as you can. So first one we look is something known as a weighted graph. Okay, weighted. So weight, just like weight, spelling it W-E-I-G-H-T. So weighted graph. Okay. So graph is weighted if its edges have been assigned some non-negative value as weight. A weighted graph is also known as a network. You can look at this graph here. Graph, this example here. Each edge has been associated with a non-negative number. Okay. So these numbers are known as weights. Okay. And there's some direction that is associated, you can see. So this is a weighted directed graph. Okay, weighted directed graph. So or it could be known as a directed graph. It means the same thing, directed graph or weighted directed graph. Weighted directed graph. Okay, normally it will be written like this so that you understand the difference between directed graph and weighted directed graph. Okay. So weighted directed graph means there is some numbers or some weights associated with the edges. Now these numbers could represent the distance between two cities, okay, or the hours to travel between two cities. So if say V0 say stands for Kolhapur, okay, this node here stands for Kolhapur, and say this node here stands for Panjim. I could say from Panjim to Kolhapur, say it takes 4 hours to travel. Okay, so therefore I would put here distance as 4. So your graphs could be used for something like this to represent the hours between the cities. So here you could have had another city, say Pune, and you could say that from Pune to Kolhapur it takes 8 hours to travel. Okay, say from Kolhapur to Pune it takes 9 hours because of some problem. Okay, so like that you could be representing the graphs. The next definition that you need to know is a subgraph. Okay, so if you take any two vertices, this is the 4 vertices are given in G1, but I'm just considering a part of the graph. Okay, this part of the graph, and this will be known as a subgraph. So just like your tree, you had a lot of nodes. Okay, in your tree you had left subtree, right subtree. Okay, you would consider a part of the tree that would be known as a subtree. So similarly, if you consider a part of the graph, it is known as a subgraph. Next definition that you need to know is adjacency. Okay, so basically adjacency is a relation between two vertices of a graph. A vertex V is adjacent to a vertex U if there's an edge from vertex U to vertex V. Okay, so you can consider any graph from here. So let's consider this graph. Okay, so if I want to say that this vertex V0 is adjacent to this vertex V3. Okay, how do I claim that it is adjacent? For it to be adjacent to each other, there should be a edge connecting them. Okay, there should be a edge. Since there's an edge connecting V0 and V3, I will say V0 and V3 are adjacent to each other. Okay, I hope you're getting what I'm trying to tell. Now in this diagram you can see here V0 is not having any edge to V1. Is not having any edge to V1. So therefore V0 and V1 are not adjacent to each other. Similarly, V0 is not having any edge with V2. This is your V2. Okay, V0 is not having a direct edge to V2. Therefore, V0 and V2 are not adjacent to each other. Here there is V3. Okay, V3 is having an edge to V2. So V3 is adjacent to V2. Okay, I hope you are getting what I am trying to tell you. What are adjacent vertices? So similarly here for a directed graph, that was the example of an undirected graph. Same definition. Okay, same definition. So here you can say, if in a digraph, okay, a directed graph is also known as a digraph. D-I-G-R-A-P-H. So directed graph also will be known as a digraph. Okay, please remember that. So in a digraph, if UV as an edge, okay, that is U comma V is an edge, then V is adjacent to U, but U is not adjacent to V. Okay, why? Because there is no edge from V to U. So what I mean by that, let's see. Okay, now look at this digraph or directed graph. Okay, this is V4 and this is V0. You can see there's an edge going from V4 to V0. Okay, edge is going from V4 to V0. Therefore, I will say that V4 is adjacent to V0. Okay, but I do not have any edge going from V0 to, I don't have this edge from V0 to V4. Therefore, I cannot say that V0 is adjacent to V4. I cannot say V0 is adjacent to V4. So I do not have an edge going like this. Okay, in that direction. So as long as there is an edge going from one vertex to another, then only I can claim that that vertex, so where the edge starts, that edge will be U, and where the edge stops will be V in terms of a directed graph. So then I can say that U is adjacent to V, but since I don't have a edge going from V to U, I don't have a edge going from V to U, I cannot say V is adjacent to U. This is wrong. Okay, but here if you take this example here, okay, this example here, there's an edge going in both the directions, so I can say V0 is adjacent to V1. Okay, V0 is adjacent to V1, and because there's the edge is going in both the directions, I can say V1 is adjacent to V0. Okay, so this you have to be careful with respect to directed graphs. Okay, in undirected graph, as long as there's an edge, I can say V0 is adjacent to V1, and I could also have said V1 is adjacent to V0. That is undirected graph. As long as, what is the condition for it to be adjacent? There should be a direct edge. Okay, direct edge between those two vertices. Next definition that you need to know is, what is the incidence? So basically, in an undirected graph, if the edge UV is incident on the vertices U and V. So suppose, what is the meaning of incident edges? For an edge to be known as incident, suppose you consider this edge. Okay, the name of that edge is V0 comma V1. If I ask you on which vertices this edge is incident, incident means which vertices are contained in that edge, then I will say that the edge V0 comma V1 is incident on the vertices V0 and V1 because these are part of the edge. Okay. Similarly, if I ask you which edge is incident on this vertices v1 comma v2. Okay, so obviously I have this edge v1 comma v2 which is incident on the vertices which are contained in this edge v1 and v2. Okay, so in directed graph, only in the direction of the edge you can say that it is incident. So if you consider these two vertices v4 and v0, then I can say that this edge v4 comma v0 is incident on the vertices v4 comma v0. Okay, next definition that you need to know is the path. So basically a path from a vertex u1 till vertex un is a sequence of vertices u1 comma u2 comma u3 dot 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 un minus 1 comma un such that un is adjacent to u1, u3 is adjacent to u2 dot 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 un is adjacent to un minus 1. Okay, to understand the definition it looks complicated, but it's not complicated. Okay, so let me show you. So suppose I'm asking you for a path. Okay, let's take this example of G2. I'm asking you, this is here V0. Okay, V0. There is V3 here. There is V2 here. Okay, and there is V1 here. So if I ask you what is the path from V0 to V2? Okay, so what is the path from V0 to V2? So you will find a path, V0 will be the source. You will find the adjacent vertex to V0. What is the adjacent vertex? There should be an edge connecting V0. The adjacent vertex is V3. Okay. Now from V3 you see whether there is a path to V2 because we have to go to V2. Okay. So there's a adjacent, there's a connection, there's a edge between V3 and V2. So V3 is adjacent to V2. So the path will look something like this. If I want to go from V0 to V2, from V0 I will come to adjacent vertex V3, and from V3 I will go to the adjacent vertex of V3 which is V2. So I can go from V0 to V3 to V2. So there could be many possible paths sometimes. In this example there is only one path. If we take this example here, okay, this one. So I tell you now to find the path from V0 to V2. This is V0. There is V2 here. Okay, and this is V1. There are many possible paths. From V0 I can go directly to V2. Okay, there's a direct path, direct edge is there. Okay, so that is one possible path. The second possible path is from V0 I go to adjacent vertex V1. So from V0 I go to V1, and from V1 I go to V2, adjacent vertex. So this is another possible path. Okay, and there are many, like infinite number of paths. Okay, you can try to find out in all these examples. Okay, so as such I'm not saying infinite, there are many possible paths. Okay, next is the length of a path. The length of the path is the total number of edges included in the path. So suppose I'm telling you to find a path. Let's again go back to this example from V0 to V2. So you can see that the path is this. From V0 you go to V3. From V3 you go to V2. So the number of edges, how many edges are involved in that path? There are 2 edges. So for the length of the path will be 2 from V0 to V2. So in this example, the length of the path is 2. Here, if I tell you to go from V0 to V2, you could have taken this path. Therefore, the length of the path, here there is only one edge involved. So therefore, the length of this path is 1. Suppose you go from here, V0 to V1, V1 to V2. There are 2 edges involved. So the length of the path will be 2. So the length of the path in that case will be 2. Next definition is reachable. So if there is a path P from a vertex u to vertex v, then we say that vertex v is reachable from vertex u via the path p. Okay, so you can see, for example, here in the graph G5. Okay, the vertex V2, is reachable from the vertex V4. Okay, where is V4? Here. This is V4. Where is vertex V2? Here, vertex V2. So if there is a path from V4 to V2, then we say V2 is reachable from V4. So you can see the path. You can go only in one direction. You will go from here to here, here to here, and here to here. So since there is a path from V4 to V2, we say V2 is reachable from V4. But if I told you, I had asked you whether V3, this is V3, okay, whether V3 is reachable from V4, this is V3, this is V4, okay. So is there a path from V4 to V3? Okay, there's no path. You would try to go, there's no path from V4 to V3, okay, because the direction here is in this direction. This edge is directed this way. I cannot go from V4 to V3. From V3 to V4 I can go, but I cannot go back in this direction. The edge is not there that way. Okay. Similarly, you try to find any other path. I cannot go from V4 to V3. Okay. So I would say that V3 is not reachable from V4. So there's no edge that is taking me there. Okay. All the directions are going away from V3. There's no direction which goes inside or towards V3. Next definition is simple path. So in simple path is a path where all the vertices are distinct. Okay. So all the vertices involved in that path are distinct. There's no repetition. Then we call that path as distinct. So you can take this example G12. Okay. Suppose you consider the path V0. Okay. So from V0 you're going to V1. Okay, so this V0 to V1. From V1 you're going to V3. Okay, from V3 you're going to V4. From V4 you're going to V6. Okay, so you can see here, this is the path we have taken to reach to V6. All the vertices involved in the path are not repeated, they are distinct. Okay, therefore we will call this as a simple path. But suppose I was going from here, I would continue the path. Okay, so I would have gone from V0 to V1, V1 to V3, V3 to V4, V4 to V6, and now I continue from V6. I go back to V3. Okay, then from V3 I am going back to V2. Say I'm going to V2. You can see here the node here V3 is repeated 2 times. Okay, I have gone from V0 to V1, V1 to V3, V3 to V4, V4 to V6. From V6 I have gone to V3, and from V3 I have gone to V2. This vertex has been repeated twice in the path. This is the example of a not a simple path. So the vertices are repeated, no distinct vertices in that path, then we call it as not a simple path. Then next definition you need to know is what is a cycle. What is a cycle in a graph? So in a digraph, a path u1, u2, un minus 1, un will be called a cycle if it has at least 2 vertices and the first and the last vertices are the same. Okay, you can look at the graph G7 here. Okay, and I tell you to find a path, and if the starting and the ending node can be the same, okay, if the first and the last vertex will be the same in the path, then we can call that as a cycle. So you can see here I can go from V0 to V1 using this direction, V0 to V1. Okay, and using this, I can go back to V0. Okay, so I went from V0 to V1 using this edge, and using this edge from V1 I can go back to V0. So where the starting edge, you can see here starting vertex and the ending vertex is the same, that is the example of a cycle. Okay, in a directed graph. In an undirected graph, okay, a path u1 comma u2 dash 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 un minus 1 comma un will be called a cycle if it is having at least 3 vertices and the first and the last vertex is the same. So you can see in a graph G12, okay, that is this graph here G12, okay, the path V1, okay, V1 to V4 to V6 to V3 and back to V1 will be a cycle. Okay, why? Because there are at least, I told you there should be at least 3 vertices involved. Okay, now the length of this path is, there are 4 edges, 1 2 3 and 4. Length of the path is 4, so therefore we can say it is a cycle of length 4. Okay, because there are 4 edges that are involved in the path. So why we are calling it a cycle? We are starting from here and we are ending back there. Okay, like that you can look at this graph and there are many cycles. Okay, there are many cycles. I could have gone from V0 to V2, could have gone to V2 to V3, I could have gone to V3 to V6, okay, and I could have gone from V6 back to V2. This would have been another cycle. There is more than one cycle in this graph. So cycle basically means you're starting from a node and you're finding a way of coming back to that node. Okay, so in that case that will be a cycle. So what is a cyclic graph? A graph that is having one or more cycles is called a cyclic graph. So in these examples on this slide here, the graphs G1, G3, G7, G9, G11 and G12 are examples of cyclic graphs. You can look at all these graphs, you will find at least one cycle. Okay, at least one cycle, then it is known as a cyclic graph. A cyclic graph is a graph with no cycles. Okay, so a graph with no cycles will be known as a acyclic graph. So the examples are G2, G4, G5, G6 and G8. There are no cycles here in these graphs. Okay, it's not possible to go back to that starting node. So suppose you start here from V0, okay, you go to V3, you go to V2, but it's not possible to go back to V0, so therefore there is no cycle. But suppose I had an edge like this, I had one edge like this, I would have gone from V0 to V3, V3 to V2, V2 back to V0. Okay, then I would have said there is a cycle. If there are no cycles, it is a acyclic. So right now it is acyclic graph. So a directed acyclic graph is represented by the acronym DAG. Okay, a directed acyclic graph will be represented by this acronym. Okay, and G5 is an example of a directed acyclic graph. There is directions and there is no cycles, so it is known as a directed acyclic graph. Next definition you should know is what is the degree. What is the degree of a node? So basically, in an undirected graph, the degree of a vertex is the number of edges incident on it. Okay, number of edges incident on it. So if you take this graph G12, I tell you to find the degree of this vertex V0. So you find all the edges that are containing it. Okay, so you can see that there are two edges that are containing V0. Okay, incident means number of edges that contain this vertex V0. There are two edges that contain V0. V0 comma V3. Okay, V0 comma V3, that is this edge, and V0 comma V2, which is this edge. Since there are two edges which are incident on V0, so therefore we will call the degree of V0 as 2. Degree of V0 will be 2. Okay. So similarly, degree of V1 will be 3. Okay. You can find out all the edges of V1. This is V1. Okay. So there is one edge, second edge, third edge. Three edges will contain V1. Therefore, the degree of V1 will be 3. Okay. Degree of V2 is 4. Okay. There are 4 edges contained. This is V2. 4 edges which contain V2. So and so on. Okay. You can find out for the others. So in a digraph, each vertex has something known as an in degree and a out degree. Okay. So the degree of a vertex in a digraph means directed graph. So in a directed graph, the degree of a node is the sum of the in degree and the out degree. So let's see what is the meaning of an in degree. Okay. So in a directed graph, the in degree of a vertex B is the number of edges that are entering the vertex B. Okay. So example, you take this graph G8. Okay. So the in degree of V0, how many, this is V0. Okay. This is V0. How many edges are entering V0? Okay. There is no edge which is entering V0. So therefore the in degree of V0, is 0. For V0, the in degree is 0. No edges which are entering V0. But if you are told to find the in degree of V1, here there is one edge, it is entering. Okay, it's entering V1. Here there is one edge entering V1. Okay, any other edge which enters V1? No. You can say the in degree of V1 is 2. Okay. Similarly, there is a definition known as out degree. Out degree. So out degree is nothing but the number of edges that leave that vertex. Okay. So if you are told to find the out degree of V0, there is one edge that leaves, second edge that leaves, third edge that leaves. So therefore the out degree of V0 is 3. Okay. So this is the way you calculate the in degree. In degree is the number of edges that enter. Out degree is the number of edges that leave. So now if I tell you to find a degree of V0, so it is the sum of the in degree plus out degree. So here we have found the in degree of V0 is 0 and out degree is 3. So the sum of that 0 plus 3 will be 3. So for a directed graph, for each vertex, if you want to find a degree of a vertex, you first find out the in degree, then find out the out degree, then you find out the sum, and the sum will give you the degree of that node. Okay, that is for directed. For undirected, I have already told you how to find. Next definition that you need to know is what is the source. So vertex which has no incoming edges but only has outgoing edges is called a source. So the in degree of a source is 0. Okay, the in degree of a source is 0. The other definition for it. So for example, in this graph G8, we saw that V0 is having in degree as 0. So therefore V0 is an example of a source. Okay. Similarly, V5 Okay, V5, the in degree of it is 0. So V5 is also example of a source. This is V5. The next definition you need to know is sink. S-I-N-K. Okay, S-I-N-K. Sink. So sink is a vertex which has no outgoing edges but only has incoming edges. Is called a sink. So in example of a sink, or the other definition of a sink is the out degree of a sink is 0. So in a graph G8, V3 is the example of a sink. Okay, it has no outgoing edges. All the edges are incoming. Okay, so this is the example of a V3. V3 is the example of a sink. All the edges are only incoming. Okay, no outgoing edges. All the edges are incoming. Okay, so that is known as a sink. In other words, the out degree of that vertex is 0. Next definition is pendant vertex. So pendant vertex is a vertex in a digraph if the in degree is equal to 1 and the out degree is equal to 0. Okay, so if you find any such vertex, then you will call it as a pendant vertex. In degree is equal to 1, out degree is equal to 0. Next definition is isolated vertex. If the degree of a vertex is 0, then we call it as a isolated vertex. Okay, so for example, here in this graph G2, V1, the degree of V1 is 0. Okay, therefore we will call it as a isolated vertex. This is a isolated vertex. Next definition is successor and predecessor. So in a digraph, that is a directed graph, if a vertex V is adjacent to vertex U, then V is said to be the successor of U, and U will be called as the predecessor of V. Okay, so if you consider this graph G8, okay, and you consider this edge, okay, V0 to V1, then V0 is called, this is V0, V0 is the predecessor of V1, okay, and V1 is called as the successor of V0. Okay, so successor and predecessor is only with respect to a directed graph. So maximum edges in a graph. How to calculate maximum edges in a graph? So if you know the number of vertices, you can calculate the maximum number of edges that will be there in the graph. So n is the total number of vertices in the graph. Then an undirected graph will have n into n minus 1 divided by 2 edges. Okay, that will be the maximum number of edges it will have. This is for undirected graph. But for a directed graph, the formula is different. So if you are having n vertices, then in a directed graph, the maximum number of edges that can be possible is n into n minus 1. Okay. So you can apply the formula and you can see. So suppose you give n equal to 3. For an undirected graph, you will have, you can apply the formula and you can check, you will have maximum 3 edges. Okay, then apply this formula and see. 3 into n minus 1, 2. Okay, so 3 into 2 is 6, and 6 divided by 2 will give you as 3. The maximum number of edges that you can have is 3 if the n is 3. Similarly, you can apply for directed graph. You will get the number of edges. Then next definition, complete graph. A graph is complete if any vertex in the graph is adjacent to all the vertices of the graph. Or we can say that, in other words, there is an edge between any pair of vertices in the graph. Okay. So a complete graph will contain the maximum number of edges. What do you mean by that? The formula that I gave you. So undirected graph with n vertices will have n into n minus 1 divided by 2 edges, and a directed graph with n vertices will have n into n minus 1 edges, and all possible edges will be there. Okay. So here in this G11 is an example of complete graph. Next definition, multiple edges. Okay, multiple edges. So if there's more than one edge between a pair of vertices, then we can say that those edges will be known as multiple edges or parallel edges. You can see this graph G tree. Okay, there's one edge here and there's another edge here. Okay, so there are more than one edge between the same pair of vertices, therefore they will be known as multiple edges or parallel edges. Okay, next definition is a loop. So an edge is called a loop or a self edge if it starts and ends on the same vertex. Okay, you can see here in graph G4 there is an edge that starts and ends on the same vertex. This would be known as a loop. Starting and ending on the same vertex. Next definition is a multigraph. A graph which contains a loop or multiple edges, it will be known as a multigraph. Okay, so G3 and G4 are examples of that. So this here is having a loop, so therefore it is known as a multigraph. Here it is having parallel edges or multiple edges, therefore it is known as a multigraph. A graph which does not have a loop or multiple edges is called a simple graph. Next definition, regular graph. A graph is regular if every vertex is adjacent to the same number of vertices. Okay, so you can see G1 is the example of a regular graph. Every vertex, you take any vertex, okay, you take this V0. How many vertices is adjacent? Is adjacent to V1 because there's an edge from V0 to V1. It's adjacent to V3 because there's an edge from in this direction, and it's adjacent to V2 because there's an edge. So it's adjacent to 3 vertices. Like that, you take any other vertex, it will be adjacent to 3 vertices. Take V2. V2 is adjacent to V3, V2 adjacent to V1, V2 adjacent to V0. So this V2 is adjacent also to 3 vertices. If every vertex is adjacent to the same number of edges or adjacent to the same number of vertices, we will call it as a regular graph. Next is a planar graph. A graph is called planar or planar if it can be drawn in a plane without any two edges intersecting. Okay. Null graph. A graph which is only having isolated vertices is called a null graph. So these were a lot of definitions with respect to just this page. Okay, students. So I'll just stop the recording.